This is a soft display powered by air. It uses 3D printed fluid logic to control its 64 pixels. Let me take you on a journey from humble beginnings through tiny wonders to a full matrix that might actually be a robot. Part of this video is sponsored by PCBWay. Our first air-powered display was this 4x4 dot matrix. We refined the design and built the segment display. Both these displays relied on 3D printed fluid logic circuits. Think of them like printed circuit boards, but for air. They contain tiny channels and together with a soft silicone membrane allows us to replicate key electronic components. Instead of electricity flowing between positive and negative, these are powered by a stream of air between the atmosphere, the air around us, and this vacuum pump. By encoding atmospheric pressure as a 0 and vacuum as a 1, we can build surprisingly complex air-powered digital logic circuits. This ring oscillator, for example, it cycles automatically, powered by a single constant stream of air. The design is inspired by microfluidics research from the early 2000s, but adapted for filament-based 3D printing. 3D prints are notoriously porous. To make them airtight, we print hot, slow and over-extruded. Switching to a glass bed creates a super smooth surface, which is key to sandwiching the membrane. This is actually how we construct our vacuum-powered transistor. But why vacuum? Vacuum pulls the membrane. Let's have a look inside the transistor. Applying vacuum to a control chamber opens the connection between two flow channels. And vacuum seals itself. Combine the transistor with a pixel. When opening the transistor, vacuum charges the pixel, a bit like a capacitor. When it closes, the trapped vacuum seals the membrane even tighter. This is how we can store a state. But these air-powered displays do contain electronics. The vacuum pump and a few solenoid valves. But those valves aren't plugged directly into individual pixels. Instead, they send air signals into our 3D printed multiplexing circuit, which decodes them inside the display. This lets us control dozens of pixels using a handful of valves. And the results are mesmerizing. The original dot matrix had only 16 pixels. The segment display was a step up with 28 segments. For this new build, I wanted to go even bigger, 64 independent pixels. And I want to be able to play Snake on it. But packing that level of density into a fluidic system meant our hardware needed some serious upgrades. To house the display, I designed a transparent enclosure. Which brings us to today's sponsor, PCBWay. You probably know them from custom printed circuit boards, but they also offer a full range of rapid prototyping services, including CNC machining, sheet metal fabrication and high-resolution 3D printing. For the enclosure, I opted for their clear SLA resin with spray varnish finish. Simply upload your CAD file to PCBWay, you get an instant quote, and a few days later, this box arrived. Safely packed inside was this gorgeous enclosure. The clarity is incredible. It's going to be perfect for showing off all the components inside. A huge thanks to PCBWay. Their support allows me to dedicate my time on these projects. Use my coupon code on your next order and save $10. To claim it, use the link in the description. Now it's time to fill this empty shell with life. Before going all in on the big matrix and to test all hardware upgrades, I decided to build a smaller version first. This is what I came up with. All components are mounted to the surface of a baseboard. Together they form the multiplexing logic core, composed of these long row channels and the vertical column channels that cross the membrane. At each intersection sits a pixel. Row, column and pixel form a transistor, allowing us to open the connection between pixel and column via the row channel. Let's start with the memory screen. It's made of 4 parts. Starting with the memory board. I printed it from transparent PLA. Each of these pins will eventually feed into a pixel. Printing on glass makes the surface so shiny. Inside you can spot the 4 column channels. Next, we cast the screen. To do so, I weigh out platinum cure silicone and mix it thoroughly. Then pour the silicone into a mold. After curing, we can demold it. And here is our finished soft screen. To combine memory board and screen, we build this little sandwich. Then press everything together. In my experience, this press-fit approach creates quite airtight pixels. For the logic membrane, I wanted to try out these commercial ones. To cut it to size, I use a printed mask and punch the through holes. With the help of an alignment jig, we carefully transfer the membrane. And here I tried to roll out the trapped air. This is a finished memory screen. Now, let me show you why it's named this way. When we press a pixel, it latches. Let's repeat that. One more time. Looking from the back, we can see what's happening when I press a pixel. The air is pushed out, and the vacuum is sealed inside, keeping the screen pulled in. One more look from the back. This memory is key for our multiplexing. If I keep staring at the pixels, they sometimes seem to invert. By lifting the membrane, we can override the pixel states and draw a new image. Now onto the baseboard. These thin prints come out quite transparent. To get vacuum power into the board, I'm using this printed lure lock adapter. These connections are standard in the medical field, so you can easily use off-the-shelf fittings, like this barbed one, for soft tubing. We can fit an O-ring, and it screws right onto the surface of the board. So far, I've used these very affordable solenoid valves. They have 3 ports, and energizing them switches how they are connected. But mounting them always required some kind of tubing. Not only do these new ones look much slicker, the connections are located right next to each other, surrounded by this little gasket. Using 2 screws we can mount them. By adding all 8 solenoids to the board, each valve receives vacuum and atmospheric pressure. And their outputs feed directly into the column and row inputs of the multiplexing core. Let's give them a quick run with the test membrane. First we have to connect the vacuum pump and the solenoid valves to the microcontroller. Every time a solenoid turns on, its LED lights up, and we can see the output switch from atmosphere to vacuum, pulling the membrane in. Let's finish the assembly by mounting the screen to the baseboard. Now, how do we write to the screen? Initially, all channels rest at atmospheric pressure. To start, the columns, our data in, are set to specific pressure levels. Then, the first row is switched to vacuum, opening all transistors along its length and writing to the connected pixels. Since each pixel acts like a memory cell, the data is preserved. By repeating this for each row, we can write an entire image. Let's try it. It works, and it looks so good. This way we can draw all sorts of static bitmaps. Onto something more dynamic. A snake. This one moves randomly across the soft screen. If you observe the solenoids, you can see that only the rows that change are updated. With this small 4x4 matrix working, let's finally move to the big one. This is the stack I came up with. I moved the solenoids to the back. Directly in front of them sit the vacuum and atmosphere supply channels. Their outputs feed into the row and column channels. Together they form the baseboard. The column channels continue through the membrane. And with the pixel channels, they form the memory board. Finally, the pixel chambers are created by the silicone screen. Quite a complex assembly. Now let's go on printing the boards. Both of these took about a day to print. On the back you find the Lure Lock vacuum power connector and the openings for mounting all 16 solenoids. Turn it around and we are greeted by that smooth surface. And a lot of openings for screws and the transistor control chambers. When holding it against the light, you can see the channels inside. Now onto the memory board. Only at this point I realized the true scale. Each of the 64 pixels has to seal perfectly, and each of the 64 transistors open reliably. Let's see if we can make it work. By now you know the drill. Cut and punch the membrane. Transfer it to the memory board. And finish the sandwich by screwing it together. Then cast the screen and demold it. Finally, we make us another sandwich and press everything together. Pressing pushed in most of the pixels. The remaining I tried to manually latch, but some refused. Nevertheless, let's find out what this assembly of silicone and PLA can do. By using my shop vacuum and pressing it against a row opening, we can manually open those transistors, allowing atmosphere to enter the pixels. So at least this part seems to work. To test it for real, we add the solenoids. While overall the display seems to work, there were many issues, and fixing these spiraled me into a deep rabbit hole. Let's talk about roughness. At the micro scale, printing on glass results in an extremely smooth surface. That smoothness lets the silicone membrane adhere through molecular forces and is key for sealing the transistor. Realizing this, I abandoned the commercial silicone sheets and went back to casting my own. You can see the difference. First, the commercial one. It spontaneously spreads on the surface. Now the self-cast one. It just keeps spreading. At the macro scale though, printing introduces thermal stress. We all know this as warping. Looking through the glass build plate, you can actually see it. Some areas are still connected, while others have detached, and in between we can see these rainbow patterns. These are known as Newton's rings, caused by interference of a thin air film. I'm less concerned about the rainbow areas, as they indicate a tiny air gap. Much more concerning are the areas with no rings. To flatten the memory board, I put on a TPU protector and place it against a sheet of glass inside a vacuum bag. As pressure drops, it is clamped uniformly. To set this shape and release internal stress, I anneal it, heating the whole bag on the bed of my printer for several hours, then cooling it down under continuous vacuum. It works surprisingly well. For the base board I used another technique. I added tiny concentric rings around the transistor control chambers, then used the same vacuum annealing trick to flatten those rings. These rings minimize the contact area against the membrane, hopefully making the system more robust. With all these changes implemented, it's time to add the electronics. The solenoid driver boards, as well as the vacuum pump and microcontroller. Attached to the display is this little backpack. Now we can finally place it in the enclosure. Add the screws and bring it to life. Starting with some simple text. It's quite satisfying to see the letters take shape row by row. Numbers are quite fun too. Next, some animations. A beating heart. And the eye. Then this cute little guy. That can get quite angry. And sad. But always turns happy again. I've also played with procedural animations, like this fire. And my personal favorite, water ripples, traveling across the screen. To build some more interactive apps, I connected this old controller. Starting with a simple walking pixel. Press X and you can draw a trail. Press circle and it resets. Quite fun. From there I moved to Pong. This is really pushing the speed limit of the display, but it works. And finally, Snake, which is surprisingly playable. This is a physical display. You can touch and feel the screen pulling on your skin. Each pixel acts like a tiny suction cup. Let me show you. Seeing this is a reminder. This display is actually a robot. And this is just the beginning. What else do you think it could become? Let me know in the comments. See you in the next one, and stay soft.